Yeah. Okay. You may also record the lecture, so everyone can record. So that's not prohibited. I even encourage you to keep the recording if something fails from my side. But I hope that I have learned all the bugs I have encountered, everything now. Okay. Let's go on. And so the main topic is stochastic integral. Stochastic integral. Stochastic integral. But I think I'd like to finish a small detail that I didn't finish last time because the time was up. Okay, the last detail. We have learned time inversion. Time inversion is a useful way to make from Wiener process. From Wiener process, we make a new Wiener process. Let's say YT. That is also Wiener process. We make a Wiener process from Wiener process, and because there are a lot of properties like variance, covariances, expected values that we know for Wiener process, then that's a useful transformation. Let's study one more problem. Example, how we may use time inversion. Let's calculate the variance of W5 given W7, where WT is a Wiener process. Wiener process. And once again, I see that I need to understand some properties in the past, given that I know some information in the future. So that's a good moment to use time inversion. So I use time inversion. I say, if you remember how we have constructed YT, YT was T times W1 over T, or 0 when T is 0, and the main formula is valid for positive T. So that's the definition of time inversion. On the plot, time inversion is very strange operation. So you have a trajectory of Wiener process, and you transform this trajectory. You transform the whole trajectory by using a strange reflection. That's not an ordinary reflection. You have a point t equal to 1. You keep this point t equal to 1. You see that for t equal to 1, y1 is equal to w1. So you keep this point and you pack this infinite part of the plot to finite interval, and you expand this finite interval into infinite interval. So that's very strange operation. For example, if you have infinitely many zeros, if you have infinitely many zeros, zero crossing to the right of 1, when you do the time inversion, every zero will be packed here. Yeah, so all these zero will be packed there, and this part, so that's difficult to show, but basically something like this part. I have something like this, and that was below 1, below 0, so I continue below 0. So that's a very strange transformation, but it keeps Wiener process, but it keeps all the properties of Wiener process like variance, covariance, expected value, probabilities, and so on. So how shall I do this exercise? I shall say, okay, And if you do inversion twice, you get the original process. Yeah. If you do the time inversion twice, so if you just multiply t by y 1 over t, you will get t times what is y over t? That's 1 over t times w1 divided by 1 over t, and you will get wt. So inversion applied twice restores the original process. So it's really like reflection, but ordinary reflection keeps the sizes of the object. Yeah, if you do ordinary reflection, yeah, if you have a hedgehog here, ordinary reflection creates a hedgehog there, yeah, with the same size. That's an ordinary reflection. Yeah, exactly the same hedgehog. But if you do this time inversion, infinite part of the line changes with the finite part of the line. That's very strange. But it has some properties of the reflection, like if I apply inversion twice, if I do WT, I do time inversion, I get YT, I do time inversion, and I recover WT. That's some kind of reflection, but not a reflection. Okay, so how may I solve this exercise using time inversion? I say, okay, I need the variance of W5 given W7. I apply time inversion. That's variance of 5 times Y 1 over 5, given that I know 7 multiplied by Y 1 over 7. And now 1 over 5 is after 1 over 7. Yeah, I have, so here 5, 7, the order of moments of time has changed. Yeah. Now I take out 5. I take out 5. Oops, I take out 5. So I get 5 square root variance of y 1 over 5 given, no, I have not enough space there. So I have 5 square root variance of y 1 over 5 given 7 times y 1 over 7. I just remove this 7 completely. Yeah, I just remove it completely. It plays no role when we speak about information. Yeah, why I can remove this 7? Because sigma algebra generated by y 1 over 7 is exactly the sigma algebra generated by 7 y 1 over 7. If there are two guys, one guy, Andrew, knows the value of y at the time moment 1 over 7, and Boris knows the same value multiplied by 7, the information is exactly the same. Yeah, because if I have two guys, one guy knows the value of y 1 over 7, and the second guy knows the same value multiplied by 7, the information they possess is exactly the same. They can follow the forecast of any random variable will be the same. So I just remove it here. And then I use another trick we have already used. So we have 25 variance of y 1 over 5 given y 1 over 7. But yt is a winner process. And we use another powerful idea. We can say that future value is past value plus change or increment, and hence we say 25 times variance of y1/7 plus the increment y 0.2 minus y1/7. y1/7. So this is fixed. Yeah, this is fixed. So this term doesn't influence variance. I got 25 times variance of y1/5, 1/7. Then, if you remember the properties of Wiener process, the increment is independent of the past value. The past value. Increment is independent of the past value. Hence, I can omit conditioning and I get variance y1/5 minus y1/7. And who remembers the assumptions of Wiener process? For Wiener process, yt minus ys has which distribution? Who remembers?
Like it's normal.
Yeah, it's normal. Exactly. What is the expected value? What is the variance?
Okay, the expected value is, okay, it's a normal distribution of 0, t minus s.
Exactly. So in my case, I have 25 times 1/5 square. Oops, sorry, 1/5 minus 1/s. That's all. I hope you can do arithmetics. That's not interesting. Okay, we have done. We have used two tricks. One trick is to decompose future value into past value plus change, and the other trick of the trade is time inversion. Yeah, we have used two tricks to solve problems, and we see that time inversion transforms Wiener process into Wiener process. And now let's start the main topic, stochastic integral. That is also a transformation of Wiener process. We will create martingales from Wiener process. So basically, stochastic integral. So we have Wt. We have stochastic integral. And we will obtain a martingale here. Many martingales, because we can use different integrals. Okay, that will be our new transformation. Let's start. Probably you know some meanings of the integral. Probably you know that. So let's go back to the school and let's discuss some meanings of the stochastic integral. So probably you know one meaning. So let's go back. So we go back to deterministic case. So let's go back to deterministic case. If you have some function f of t, probably you know how to interpret integral from a to b. Yeah, probably you know how you may interpret integral from a to b of this f of t dt. You should know at least one or two interpretations. Anyone? How can we interpret? Okay, that's area
It's area under the curve.
Okay, that's area under the curve. That's the first interpretation, geometric interpretation. Probably you know about physical interpretation that if you treat that f of t is the velocity, yeah. If you say that speed, velocity, yeah, velocity at time t, then probably you can say that integral from f of t dt is equal to anyone. What is the meaning of the integral if f of t is velocity, the speed?
It's the difference, like.
Yeah, it's the distance traveled. Yeah, the distance you travel. So the distance you travel. And the third, so there are many more interpretations, but one that is completely unknown, and I don't know why. It's not discussed in school, and you have not discussed it during your first, and you have studied calculus at high school of economics, and you don't know the economic interpretation of the integral. So that's pity. I don't know why things are like that. You have studied calculus in high school. Now I will tell you the interpretation from economics, and we will use it. It's very important in finance, and and we will apply it to winner process. But first, we need interpretation. Okay. Finally, we may say, let's look here in this integral. We have two functions. Yeah. If we look carefully, we have two functions, f of t and dt. For the moment, I will separate these two functions. I will say integral from a to b. I will write the first function as q of t, and the second function I will write as p of t. And in my example, for example, if you consider integral from a to b, let's say t squared dt, and then in this example, q of t is t squared and p of t is just t. Yeah, I have two functions in the integral. So if you look carefully, you see that there are two functions. Yeah, normally you say, oh, we have only one function. No, we have two functions. So if you look carefully on the integral sign, you have two functions. You have one function one, and you have here function 2. Okay, so as the probably as my notation suggests, we will use this as a price of an asset, price of the asset. I don't know which asset. Maybe it's the price of book, the price of an apple, the price, the dollar price. I don't know. And this is the basically my trading strategy. How many shares or how many bonds or how many apples I keep in my house, or how many dollars I have at time moment. So that's my trading strategy. So that's my trading strategy. What do I mean by trading strategy? Trading strategy prescribes how much should of the asset should I possess. Let's consider some specific examples. So let's and finally the meaning. Yeah, the meaning. This integral a b from a to b q of t d p of t. That's just the profit. Just profit. The net profit. Net profit. If you use this financial strategy, and this is the price of an asset. Let's check that this interpretation really works. So let's check this. My interpretation is indeed correct. So let's first interpret the integral from to 7, 5 dt. Once again, I'm using interpretation from economics. Yeah, I know well that you can integrate this integral from 5 times dt. You can do this, but pay attention to the interpretation, because we will transfer this interpretation to the case of Wiener process, and there all the integration techniques will fail, but the interpretation from economics will work. So I believe that you can just blindly multiply 5 times t, put 7, put 2, and that's okay. But pay attention to the interpretation. That's important. Interpretation is important. Okay, let's see what happens. What happens? I have two functions. First warning, I have two functions. The first function describes the price. This is the price function. This is t. This is p of t. This is price. And the price just increases monotonically. Yeah, from time t to time 7, the price goes up. Yeah, the price goes up. I don't know, maybe there is inflation or something else. And my trading strategy is boring. I just keep 5 units of an asset. Yeah, I don't buy, I don't sell. My strategy, keep 5 units, 5 shares or 5 apples, I don't know. That's the quantity, Q of t. And my trading strategy is very simple. Keep 5 units, keep 7, keep 5 units of an asset. Yeah, that's quantity. Yeah, quantity. Q quantity, P price. So let's calculate the profit. My trading strategy prescribes me to buy 5 units of an asset at time 2. Okay, what will be my net profit? My net profit will be, okay, at this moment of time, I should buy 5 units, and the price of each unit is 2. Initial price of each unit is 2. So I should pay, if I buy 5 apples, I pay minus 5 times 2. So I buy 5, let's say, apples at time t equal to 2. Okay, then I just wait. I have no transactions in between initial moment of time and final moment of time. And then the time ends, and I sell all my 5 apples. They do not disappear, so they are ideal apples, so I have no loss. And so I sell them. I sell 5 apples. I sell 5 apples at time t equal to 7, and I got 7 times, 5 apples, but the price has increased. Yeah, the new price is 7. Yeah, and basically, obviously, the result of integration is 25. But my point is in interpretation. Yeah, I have a new interpretation. Okay, that's fine. Any questions? Anyone? Is it clear?
Questions?
Okay, now that allows me to integrate, that allows me to understand. So when you have done in Calculus Plus, probably you have done the following trick. Yeah, probably you have done something like, okay, t times 2t times dt. You said, oh, you can move this 2t there. You can say that's 1 times dt squared. Yeah, probably you have done tricks like this. During your calculus course, and basically that has economic meaning. Yeah, instead of changing the trading strategy, you can change the price. That's basically, you can interpret this in terms of trading strategy and price change. Okay, but I will not go there. I will just say that now I can integrate with respect to winner process. If we keep this interpretation, then we can do this exercise.
Can I ask a question?
Yeah. Yes.
So you wrote that from a winner process we can create many martingales by using stochastic
and
integral, right?
we will do this now. Yeah.
But we also discussed like creating and coming up with martingales is a very hard task. So does understanding of a stochastic integral makes this task easy or maybe doable in finite time?
Yes.
Okay, thank you.
Okay, so the exercise using, so I do not provide formal definition for the moment. Okay, using economics interpretation of integral, calculate integral from 0 to 10 yt dwt, where yt is equal to 2 for t from 0 to 7, and 9 for t from 7 up to plus infinity. I don't care what happens after 10. Okay, let's calculate this exercise. Let's calculate this integral. Okay, once again, pay attention that we have two functions in the integral. This is the first function, that is a quantity function or trading strategy. That's quantity. That's quantity. That's the price. My price is random now. Yeah, it may go up, it may go down. That's a winner process. And the quantity is deterministic, but maybe you can guess that we can introduce randomness into quantity. You can take one decision if something goes bad, and other decision if something goes well. Okay, so let's calculate this integral. Once again, pay attention that you have two functions in the integral. Not one, you have two functions there. Okay, we have the quantity function and the price function. The price function is random, so I will sketch just one possible trajectory. So that's just one possible trajectory. There are many other possible trajectories, and the quantity function is deterministic. Yeah, that's for sure. It will be 2, and from 7 we will have 9. Yeah, that's a quantity function. That's yt. Okay, now let's integrate. Okay, first, what happens at time moment 0? At time moment 0, I need to buy. So what happens at time t equal to 0? At time t equal to 0, I buy 2 apples. So the number of apples, I need to buy initially 2 apples. I buy 2 apples. How much should I pay? I should pay minus 2 times W0. The price function is W. 2 is a quantity I need to buy. Okay, what happens at time t equal to 7? What happens at time t equal to 7? According to this financial strategy, yeah, I should have more apples in my portfolio. Yeah, in my portfolio, I had 2 apples before, I had 9 apples after this moment of time. Hence, I should buy 7 apples. Yeah, I buy 9 minus 2 apples more. Yeah, because my quantity function says that I should, before this moment, I should have 2 apples. After this moment, I should have 9 apples. So basically, I should buy 7 apples at this moment of time. If I buy 7 apples at this moment of time, so how much should I pay? I buy 7 apples, 9 minus 2 is 7. And the price of each apple at time moment 7, yeah, is W7. And finally, at time 10, yeah, at time 10, at time t equal to 10, I sell my portfolio to calculate the net profit. I sell everything I have, all the 9 apples. I sell 9 apples that I have, and hence I will get plus 9 times the random price. Yeah, the price will be random, so I will get plus 9 times W10, and hence the value of my integral from 0 to 10 yt dwt is equal to minus 2 times w0 minus 7 times w7 plus 9 times w10. And I have calculated the first stochastic integral. This is our first stochastic integral. Our first stochastic integral. Any questions? Now we will consider some more examples, and we will see that this interpretation from economics changes the, it seems very strange, but this integral completely coincides with what you know in deterministic case, but the rules of differentiation, of integration in continuous case will be different. Any questions about this first stochastic integral? Yeah?
No.
Okay, let's move on. Let's move on. The problem is in stochastic for stochastic processes, all the rules of integration do not work. But the economics interpretation does. So that's very important. You can't just write, oh, I'd like to integrate in the integral from 0 to t, wt, dwt. Your first idea, say, oh, I remember from, sorry, that should be from, okay, from the 10 t. So your first idea may be something like, oh, I should write wt square root over 2, change t from 0 to 10, and obtain something like w 10 square root minus 2 minus w0 square root over 2, and this is wrong. This doesn't work. Yeah, that doesn't work anymore. So that's wrong. Yeah, that's wrong. First, let's understand intuitively why it is wrong. What is the main reason why this old, how it's called, it's Newton-Leibniz formula. Yeah, Newton-Leibniz formula. Newton-Leibniz formula fails. First, let's understand why it fails. Basically, what is the meaning of this strange integral? Yeah, what is the meaning of this integral? Once again, I have two functions here. I have quantity function, and I have the price function. In this more complex example, quantity function is random. This q of t now is random.
And the differential of quantity function is a price function, right?
In this example, they do coincide. In this example, in this particular example, they do coincide, but they may be different, as our previous example shows. They may be different. Yeah. So
here both WT is both quantity and price function.
Yeah. In this example, that's both quantity and price function. Yeah. In this case, that's exactly the same function. Yeah. In my example, I just like to motivate the idea why old rules of integration do not work even in the very simple case when there's the same function WT here, WT there. Why all the good friend Newton and Leibniz, why they are not with us anymore? Yeah, why they have disappeared? So first, let's go back to interpretation. We buy and sell an asset with this price. Yeah, but if you look at the increments of Wiener process, what are the properties of Wiener process increments? WT minus WS are normally distributed with mean zero and some variance, and the WT minus WS are independent of Fs of all you know up to time S, yeah, T bigger than S. Okay, what does this mean? That means that we are playing a fair game. We buy an asset, it may with probability 1/2, the price may go up with probability 1/2 because that's a normal distribution, it's symmetric. So we buy apples according to some financial strategy, and the price of our apples may go up, may go down with equal probabilities. And the second property says that you can't predict the change. Yeah, if you have information about the past behavior of the price of the apple, yeah, of W, you have the history of prices, but the future change, WT minus WS, is independent of what you know. Hence, our intuition, our financial intuition says that, okay, we are playing a fair game. Yeah, we are playing a fair game. Hence, our welfare should be a martingale. Yeah, that means we are playing a fair game. We are playing a fair game, hence the expected net profit should be zero. Hence the expected value of this integral from 0 to 10 WT dWt should be zero from our financial intuition. And if we check the value provided by Newton-Leibniz formula, that goes clearly against our intuition. That's positive. Yeah, it says, oh, you can't receive negative value, so that's wrong. And if you look at this W squared over 2 minus W0 squared over 2, that is W0 squared over 2 minus 0 squared over 2. and that's clearly non-negative. Yeah, the expected value of let me once again write the wrong guess. Yeah, that's the wrong guess. That's not the right formula. Obviously, expected value of something non-negative will be not strictly positive. Yeah, so this will be strictly positive. Now let's find the right formula. Okay, so I hope I have explained the financial meaning of the integral. I promised that all the formulas do not work. Okay, so the right question is what is the right formula? Okay, let's discover the right formula indeed in a simple case. Okay, let's find the right answer. Let's find the right answer. Okay. Well, let's find the integral from 0 to 10, WT dWt. Okay. First of all, it's a little bit counterintuitive that we are trading continuously in time. So for the moment, let's consider discrete approximation to this trading strategy. So let's imagine that I have a time from 0 to 10, right? And I split this time interval into n equal segments, and n will be very big, n will tend to infinity. So I split this time interval into n sub-intervals, okay? So this is from 0 to 10 over n, this is twice time 10 over n, this is this is 10 over n, this is 2 times 10 over n, and so on. Yeah. Or maybe let's write big T there. Let's write big T there. That will be T over n, B2 big T over n, and this is n times big T over n. And this will be the points where I will trade. Okay, so what will be my approximation? So I will say that it's approximately equal to integral from 0 to t yt dwt, and my financial strategy yt will be the following. Yt will be at time t equal to 0. Let me draw the picture. I think the picture is more, that's something like this. This is yt and wt. And I have these t over n, 2t over n, 3t over n, and so on. And my approximation is the following. First, I replace my constantly changing trajectory of WT by piecewise constant function. So my function will be piecewise constant. Yeah. So I consider approximation the blue ladder. I have a blue ladder that approximates the black continuous line. Yeah. So yt will be equal to W0 for t between 0 and big T over n. It will be equal to W t over n for t between 0, oh no, sorry, between t over n and 2t over n, W2t over n for t between 2t over n and 3t over n, and so on. Yeah. So yt approximates wt. This idea is clear. Yeah, we approximate continuous function by by a function with horizontal steps of small length. Yeah, that's okay.
Yes.
Okay, now let's calculate our integral. Let's calculate our integral from 0 to big T yt times dwt. Okay, so once again, what is my net profit? Yeah, let's calculate the net profit. What is my net profit? Okay, initially, I should buy. So I will have n+1 transactions. Yeah, I have n+1 transactions. I have n+1 transactions. Yeah, because at every moment I will do some buying or selling. Yeah, I will buy or sell apples. Okay, what is my initial transaction? Okay, first initial transaction. Initial transaction, I buy minus W0 times W0. So that's my initial investment. Okay, now intermediate transactions. Let's consider the typical moment. So let's consider the typical moment. So the typical situation, okay, this is a point like I times T over N. So that's a typical moment. We have some number of shares before, some number of apples before this moment. We have some number of shares after this moment. So let's consider the typical transaction. Typical transaction. So at this moment, so that's moment in time. So the price is equal to WIT over N. So that's the price. And now how many apples should I buy? Yeah, I suppose that I'm in a financial environment and my apples are infinitely divisible. So I speak about shares and I don't care if I should buy 0.0002 apples. That's okay. I can buy 0.0002 bitcoins or something like this. Okay, let's look at this change in quantity. That is, so that's quantity. Yeah, that's quantity. This value is WIT over N, and that quantity is WI minus 1 T over N. Let me write in bigger font because otherwise it will not be visible. So this will be WI T over N, and this will be WI minus 1 T over N. Yeah. Right. Bigger letters. Okay. So typical transaction. In this example, I buy shares, but if so the evolution of W itself, so that's a quantity function. The price function will something like this. Goes like this. Or maybe there. I don't care. Okay, the typical transaction plus J goes from I goes from 1 to N. The price of typical transaction is W IT over N. And I should buy WITN. I don't have enough space here. Okay, let me write it here. Minus W0 times W0, that is initial investment.
Why it's W0 times W0 if we have like YT and WT?
Because at time W plays two roles. It is the price of an asset and it is the quantity of an asset. So at time moment 0, what is the price of an asset? W0. How many apples should I have? W0. To have W0 apples, you should buy W apples, but each apple has a price W0. So you should pay W0, the quantity, times the price, W0. W0 plays two roles. The price of an apple at time moment 0 and the quantity you should have in your portfolio. Yeah.
We have like YT in the integral here.
Yeah. We have YT in original integral, but we have WT in the original integral, and we have replaced it with YT, that is approximation to winner process to make the number transactions in our original integral. We should trade at every moment of time. We should buy a little bit every moment of time, but this is not easy to interpret. So we consider for the moment approximation when we are buying and selling at discrete moments of time.
How we understood that we need to do approximation in this way?
You may do approximation in other way. So that's the question. You just say that, okay, you can choose other transaction points. So you can choose not equal intervals, but the idea, let's consider discrete transaction.
Well, it's just like a discretization, I think. So
Yeah.
W is non-discrete. It like has infinite values. It's like time. You can take 1 second or 1.1 or 1.11.
Yeah.
But YT is like a discretized case function.
Okay.
YT is the piecewise constant approximation to WT. WT is in black, so that is WT. And the YT is in blue. Yeah, YT is in blue. You can choose other moments. The main point that the length of these small time intervals should go to 0. You may choose unequal time intervals, but the main idea that we can easily use our financial intuition when we have a finite number of transaction points. It's a little bit difficult to imagine the continuous trading. Yeah, you may say, oh, I trade every millisecond, I can buy and sell. yeah, that's okay. I can buy and sell at every microsecond, that's okay. But continuously is a little bit, continuous function are a little bit out of our imagination, and hence to use financial interpretation, I just switch to this discrete approximation. That's okay?
Yeah, thank you.
Okay, now let's move on. That's our initial investment. Okay, now we consider all transaction points. I goes from 1 to n. The price at typical time, at typical transaction moment, the price is WIT over n. We multiply it by which value? So if I write minus there, so I write WITN minus WI minus 1T over N. So that's net profit from, okay, that's intermediate transactions, yeah, intermediate transactions. And finally, I sell everything I have. Final payoff, yeah, let's say final payoff. At time big T, the price is WT, and I have WT apples. Once again, in our example of integral, WT is the price and WT is a quantity. So at the final moment of time, I have WT apples. Each apple can be sold for WT. So my final payoff is WT times WT. Okay, that's the value of my integral. And now we should take n to plus infinity. Be brave.
What is written in curly brackets? Is it like W subscript I minus 1, or could you please clarify what is this symbol?
Yeah, this difference.
Okay. Thank you very much.
So that's how many apples should I have? I T over n minus how many apples I really have before this transaction moment, yeah? So this is the number of apples I should buy additionally, yeah? WIT over n minus WI minus 1T over n. That's better.
Thank you very much.
So once again, that is a quantity. In blue, I have the quantity. In red, I have the price. This is time. This price is WT. And hence, how many apples should I buy? The desired number minus the number of apples I really have. Yeah. Okay. Now let's make n tend to infinity. Okay. So let's take this big. Let's take this big sum. And let's take the limit. First of all, to calculate the limit, I will transform the sum a little bit. I will simplify it. So that's our integral. So that's our integral from 0 to big T y t d double ut. So first I will transform it a little bit because I have all these things are correlated. And so, for example, this thing is obviously correlated. So they are dependent, and and all the terms in this sum are dependent. And it's difficult to calculate the limit of a sum where all terms are dependent. Yeah. And it's much easier to work with independent because we know all theorems we have, like central limit theorem, law of large numbers. They deal they deal with independent terms. So first idea, go transform, more better, rewrite as a sum of independent, rewrite as a sum of independent terms. It seems impossible. Oh, they are dependent. How would I write the independent terms? From the property of Wiener process, let's recap that if we consider W, let's say 2t over n minus W1t over n, W3t over n minus W2t over n, W4t over n minus W3t over n. These are increments and they are independent. Yeah, these increments, independent increments. So that's much better to rewrite this sum using increments, and it's possible. At first it seems, oh, I have something multiplied by increment. Okay, let's do this. First, let's see. Okay, let's calculate the ideal sum. Okay, ideal sum. Let's call it A. If I consider the sum I goes from 1 to n y I t minus y I minus 1 t over n squared. So that's the sum of independent terms. The sum of independent terms. Yeah, that's the sum of independent terms. If I consider this sum of independent terms, I can open the brackets and I can see that it's very similar to what I have. Let's open the brackets. In the sum of independent terms, I have sum I goes from 1 to n wit squared over n plus wi minus 1t over n squared minus twice wit times w. Oh, I'm lazy to write all the things. Okay, so what do I have here? I have the sum I goes from 1 to n yit n squared. Oh, let's introduce probably the notation. Let's write vi instead of wit over n. Yeah, I think it will save our life. The sum vi squared plus the sum of vi minus 1 squared minus twice the sum of vi times vi minus 1. Yeah, that's okay. If I look at this sum, that sum, they are almost equal. Yeah, I may say that this is sum of vi squared from 1 to n plus the sum of vi squared from 1 to n, but this is a little bit different. The last term is absent, yeah, so I should subtract it. Vn squared, and initial term is present, yeah, plus V0 squared, minus twice the sum of Vi minus Vi minus 1. I goes from 1 to n. Okay, what do I have? I have sum of two sums of Vi squared minus two sums of Vi times Vi minus 1 minus Vn squared plus V0 squared. V0 is W0 is 0. So I can omit this guy. And finally, I know that this is sum. Basically, this is the sum of independent terms. This is the sum of Vi minus Vi minus 1 squared. And if I look at my sum, the sum I have, what is the sum I have? This I will omit, this is 0. I have minus sum Vi times Vi minus Vi minus 1 plus Vn squared. Yeah, that is the sum I'd like to calculate. And this is the sum of independent terms. Hence, I see that the Vi squared minus sum of Vi times Vi minus 1, this sum is equal to the sum of independent terms, and that's very easy to work with independent terms. I should write what I should add Vn squared and divide by 2. And now the integral I'd like to calculate is expressed as the sum of independent terms, and that's very great. That's very great idea. That's minus this sum, yeah, minus this sum plus Vn squared. Okay, so it's minus this sum, Vi minus Vi minus 1 squared plus Vn squared over 2 plus Vn squared. And hence I got minus sum of Vi minus Vi minus 1 squared plus Vn squared over 2. Okay, I've got now the expression that is very easy to calculate. Now we have law of large numbers, central limit theorem, so we can calculate all the limits. Okay, now we have expressed our integral in a very interesting fashion. So our integral from 0 to big T W, sorry, Yt times dyt is minus sum of Wit over n minus Wi minus 1 t over n squared divided by 2 plus Wt squared over 2. Now let's calculate the limit. So we have expression for which the limit is very easy. Okay, let's calculate the limit. First, we need to specify the type of limit we calculate, because when we work with random variables, you remember that there are probability limit, almost surely limit, there are different limits. When we calculate limits, there are different conceptions of limit for random sequences. There are different conceptions of limit for random sequences. In this case, we need a special conception that is called limit in the L2 space. So we will calculate L2 limit. The conception is very easy. Maybe that's not. It uses expected value. We say that R1, R2, R3, R4, and so on. This sequence of random variables converges to the random variable R in the L2 sense. According to the definition, what is required? The expected value of R minus Rn squared goes to 0. So that's the conception of the limit in L2. The expected value of the difference squared goes to 0. And now, what changes when n tends to infinity? When n tends to infinity, this term does not change. Does not change. Does not change. And this term, and the first one, we need basically to calculate the limit of this term. Okay. What we can say about this term? Okay, we need to calculate this minus sum of wi t over n minus wi minus 1 t over n squared over 2, and we need to calculate L2 limit when n tends to infinity, and we need to calculate this value. Okay, we're almost done. How to calculate this L2 limit? In general case, it's tough. Probably you know from the calculus course that even some limits, some deterministic limits during your calculus course were difficult. Yeah, probably you remember that doing something, the L'Hopital rule or something else. Now the things are much more complicated in general case. But this particular limit is very simple. Okay, let's look at it carefully. Let's just recall that we will, so this is our Rn. Yeah, this is our Rn. And we need to calculate the limit. First, let's calculate the expected value of Rn. Yeah, what is the expected value of Rn? Let's calculate the variance of Rn. And we will see that expected value of Rn is, so the expected value is easy. Yeah, so it's minus 1 over 2 n terms times expected value of wi t over n minus wi minus 1 t over n. Yeah, so to calculate expected value, we just need to calculate expected value of each term. Okay, who remembers Wt minus Ws has normal distribution with mean 0 and variance t minus s. Hence, the expected value of Wt minus Ws squared is equal to, how can I calculate the expected value of the squared increment? Anyone? The expected value of the difference squared when you have normal distribution.
It could be approximated with through variance.
No, that's just the variance. Why approximated? It's exactly equal to
right.
variance. And it's exactly equal to variance, so it's t minus s. So in my case, it's minus n over 2 times the time interval here is t over n, and that is minus t over 2, and cancel out. Okay, let's calculate the variance. Once again, I have 1 over 4, because minus 1 over 2 goes out. I have n terms, and I need to calculate the variance of these, let's call it delta I. Yeah, let's call it delta I squared, yeah. Delta I has normal distribution with mean 0 and variance t over n, yeah. So I may say how to calculate variance. I may say that delta I minus 0 divided by square root of t over n. That's a standardized normal distribution. So it's normal 0, 1. Let's write z instead of this fraction. So delta I can be written like, so is distributed like z times square root of t over n, where z has normal standard distribution, 0, 1. And if I continue my calculations, yeah, oops, variance, up. So I may say that this is n over 4 times variance of z times square root of t over n squared. So that n over 4 times variance of t over n times z squared. That goes out of the variance. So I will get n t squared 4n squared times variance of z squared. And I don't care about this value. This is constant. You can integrate with respect to, so you can calculate the variance of normal distribution squared, that's okay. But I don't care. The main point that it goes to 0. You see that I have t squared over 4 times variance of z squared, but the most important is that I have 1 over n. And clearly when n tends to 0, I don't care about this part. That's constant. I don't care about it, and it's 0. So let's recap. This strange term, this strange, ugly term, awful term, has two properties. So this, we've called this term Rn. So our final conclusion, the expected value of Rn is minus t over 2. Here we have calculated it. The variance of Rn, we have not calculated it exactly because I'm lazy to integrate, to calculate the exact value. But the main reason that the variance goes to 0. So the variance goes to 0. Okay, what is the limit? Rn is less and less volatile, has lower and lower. So if you split time interval into 1 million sub-intervals, this Rn will have almost 0 variance with expected value minus t over 2. Hence, Rn tends to minus t over 2. So that's the limit we have calculated. And hence, our answer is that stochastic integral from 0 to t of wt dwt is minus t over 2 plus wt squared over 2. This is the good formula, and that does not coincide with old Newton-Leibniz. Once again, that does not work anymore. Yeah, wt squared over 2 minus w0 squared over 2. Yeah, old Newton-Leibniz does not work. Does not work. And we have calculated our first stochastic integral for continuous quantity process, because for discrete quantity process, that's very fast, but for continuous quantity process, that's difficult. And that's perfect moment to end our practice class, because we have discovered the new world of integration with respect to new rules. And as you remember, so WT was winner process, and it was martingale. We integrated something with respect to this winner process, and we've got in our particular example, obviously, if we change this quantity process, you will get different result if you change the quantity process. But we have obtained martingale. Yeah, you remember probably that last time we have proven that WT squared minus T is a martingale. Here it's divided over 2. Here it's divided over 2, but that is a martingale. That's a martingale. We have proven that this process is a martingale, I think 1 week ago, 2 weeks ago. 1 week ago, we have proven that that's a martingale. So we have obtained a new martingale. And that's the general method that will work under some reasonable assumptions when you don't consider processes that blow up or you don't have discontinuous, that under mild technical assumptions, under mild technical assumptions, if you integrate anything with respect to the price process that is described by winner process, and you will get a martingale. And you will get a martingale, so martingale M of T, yeah, M of T, that is a martingale. And that's the very general way to create martingales out of winner process. Just use any trading strategy to buy and sell winner process, because winner process is unpredictable. It can go up, it can go down. You can use very dumb strategy, you can use very intellectual strategy, but the net profit process will be a martingale under some mild technical assumption that you do not consider something like I will sell 10 shares before the price of a share drops down by 5. Yeah, that strategy should be excluded as unfeasible. But if you exclude unfeasible strategies, if you don't invest infinite amount of money, so you will have a martingale as a result. Okay, thank you very much. I understand that calculating the limit was difficult. I understand this well. Normally, as with ordinary integrals, normally you don't calculate integrals using limits. You just have some rules, some known integrals. You have a table of integrals. You calculate them not by calculating limits. So that's maybe unique example. We have calculated by hand, yeah, from the financial intuition till the final answer. Normally, we will use properties of stochastic integral, and the main property will be Ito's lemma, but that's for the next week. Okay, thank you very much. See you next time. If you have any questions, don't be shy. You may ask in the chat or in person. Okay.
Yes,
thank you.
I wanted to ask a question. So, like, is there some specific notation for this integral? Like, for example, in some course books.
It's no, you just understand that if you write something like
If I
WT
have
squared T
a
WT
process,
from the, yeah, obviously you see, oh,
okay,
it's about winner process. Yeah, if you
okay.
see something like T squared DT, that, so we don't need some special notation. So from the context, you know, somewhere before this integral, it's written WT is a winner process. Yeah, somewhere before WT winner process, and we don't need a specific notation. We just write it like this, but we keep in mind that WT is random, and that drastically changes the integration rules.
Okay, thank you very much.
Okay, bye bye. See you next time.
Okay, I have think change.
Yeah.
No, I just was writing like questions for rechecking myself, right? About what
That's
was
good.
going on today.
That's good.
That's I just wanted you to check them, like.
That's okay. You can write in the chat. You can ask now. That's okay. I agree that self checking is good. Yes.
Well, okay, I think I'll just send them in the chat.
Okay. Yeah, that's great.
Just
As you
for
wish.
you to check how good these questions are, and maybe
Any
what I
question is
should
good.
add.
Any question is good. I strongly against the point that there are dumb questions. So I think all questions are good. Maybe explanations may be bad, but questions are good. So because if you have a question, that's a good question. That's the definition.
No, it's just like these questions, not because I don't know the answer, but more like to recheck yourself in the future.
Yeah, to check that you understand right. Yeah, that's a good type of question. I don't see why that's a bad question. Yeah, sometimes you don't know the answer, and sometimes you are in doubt. Maybe I'm wrong. Maybe I'm right. That's okay. Yes. Don't be shy. Write your questions.
Okay.
Thank you very much. I will answer. Yeah.
It's not necessary to answer. It's more like the purpose just to check how good they are, like for self-testing. I mean.
Okay. Yeah.
So okay, I just think I'll just send in private. Yeah.
Yeah. As you like.
Just a moment, then. There it is. Okay, so this is how questions look like.
Yeah, I will check. Yeah. What's the winner process? Yeah, we need to give the defining properties. Yeah, what are the interpretation of integral? Yeah. Okay. Yeah.
And this are just yes example, and also some like questions hints, understanding some midpoints of the explanation.
Yeah. I think everything is great.
Okay. No, I just also interesting to try it on myself.
Just maybe at time t buy or sell apples. Yeah, at t equal to 0 we buy them, at t equal to 5 we buy them, at t equal to sell we sell them.
So on T0 and T5 we buy them, and then on 7 we sell on them.
Yeah, because what is your trading strategy? You buy additional apples. When time ends, you sell your portfolio and you count the profit. Yeah, you buy, and at the final moment of time you sell. So that's why here basically once again so that's initial investment. Yeah, what is it? The first term, initial investment. So transactions in between, and this is a final sale. Yeah, I sell everything I have, and so this sum is my net profit. At the final moment, I sell all apples I have.
Okay. I got it. Thank you. I think I will not first notice this.
Okay, see you next time.
Yeah. See you next time. Goodbye.
Goodbye.